Hello, everyone. Welcome to this week's lesson. What we're going to be focusing on this week is the how of a chemical reaction, how exactly it takes place on the molecular level. So the essential understanding that we need for this is something called collision theory or the collision model. So I'm going to walk you through some slides and explain to you a little bit about how this collision model helps us to understand the process of how a chemical reaction works. So first of all, what you need to know is a chemical reaction can only take place when two particles, reactants, collide with each other. And the collisions that they have can't just be any old collisions. They have to have a sufficient amount of force and also the right orientation to cause this reaction to take place. To elaborate a little bit more, in any chemical reaction to be defined as a chemical reaction, bonds of the reactant particles must break and the product particles must form new bonds. So you can only have this happen during a collision process where they're breaking the individual bonds of one thing and forming new bonds of something else. So these have to have sufficient energy and sufficient orientation for that to occur. One common misconception is that dissolving is the same thing as reacting. While sometimes we can use the same kind of language to describe something dissolving in water or dissolving in another solvent, it is not a chemical reaction because you're not physically changing the bonds that were present before or making new bonds. So you can see in this diagram, we're looking at the dissolving of an ionic compound called potassium chloride here. And in this, what you can see happening is the water molecules are surrounding each of the ions in potassium chloride. The potassium over here is being surrounded by the oxygens, which are the negative side of the water, and the chlorines are being surrounded by the hydrogens, or the positive side of water. But you might notice that the bonds are hydrogen bonds that are holding them all together. They're attractive intermolecular forces. They're not new bonds. So a dissolving process is a physical change. The potassium and the chlorine ions are still present here, just as they were when they were closely packed together. Now they're just spread out and surrounded by water. So not a chemical reaction. Now back to talking about chemical reactions. Like I said before, for a reaction to take place, the reactant particles have to collide with each other with a sufficient amount of force. And there is a formal term for this sufficient amount of force, something called the activation energy. It's defined literally as the minimum amount of energy that's needed for a reaction to take place. It's symbolized with a capital E with a subscript A most of the time. The analogy that you can see in this slide here is of a golfer. If the golfer does not hit the ball hard enough, the ball will go partway up the hill and then roll back down. That would be symbolistic of a collision that is not sufficient enough to cause a reaction to take place. But with enough force, the ball will go over the hill and hopefully into the cup. That would be a metaphor for an actual successful collision that would break the bonds of the reactants and cause new bonds to form to make the products. One really useful visual model of this process is called a reaction coordinate diagram. These come with a few different names if you see them in texts. The other name that's really commonly used for them is a potential energy diagram. The reason why is because you measure potential energy on the y-axis and the reaction's pathway, or like the time course of the reaction, on the x-axis. So as you can see, for this diagram that I have right here, what I'm symbolizing is a rearrangement reaction of a compound called methyl isonitrile. Essentially, it breaks apart and reforms in a new way to form a slightly new compound. But what you can follow along with this process is that at the beginning, the reactant has a certain amount of energy, a certain amount of potential energy that's stored within its bonds. Then it collides with another molecule of itself, and you can see that the potential energy is increasing at that point. There's an active push of the two molecules against each other at this point, and eventually that causes a breaking of the bond. That's where the potential energy is the highest, because you have made the original reactant into a really high energy, kinetically high energy substance known as the activated complex. This is where the bonds have broken, but the new bonds have not formed yet. So it's a very temporary and very unstable species that lives here in the middle. The activation energy of the reaction is the amount of energy it takes to go from the original amount of energy of the reactant to this point where everything is broken apart. That's the minimum energy needed to make the reaction happen. Once it happens, then you quickly get a release in energy as the new bonds form, making a more stable structure in the end. And it drops down here to where the new product is, and it has its own level of potential energy. So a lot of really good information we can get from a potential energy diagram or a reaction coordinate diagram like this. It can show the energy of the reactants and the products, and therefore you can see that the change in energy of this reaction happens. For this particular one, the reactants have a higher potential energy than the products do. So in essence, the reaction lost energy during the course of the process. This delta E here for this process is negative. That is how we would know that this is an exothermic reaction, not an endothermic one. If you were to reverse the levels, having the products be higher on the potential energy axis than the reactants, then it would be an endothermic reaction that would take in energy overall as the reaction proceeded. A couple other terms here that are helpful. The highest point on the diagram is referred to as the transition state. It's a point in time where you have an in-between of reactants and products. And it's different than what the substance is that is there. That substance that's halfway between products and reactants is called an activated complex. These are often difficult to distinguish between each other. Transition state is just the point on the graph, whereas activated complex is the substance that appears at that point on the graph. So with this diagram, we can tell lots of really interesting things like the change in energy of the reaction, but also the activation energy barrier that's needed. And lastly, what kinds of things are happening during the course of this collision. One drawback that we're going to see with these reaction coordinate diagrams is that they're really not that great at describing a large sample of reactions happening at the same time. It's really a very focused model of what happens during one single collision between reactant particles. But if you're going to be doing experiments, you have to have a better view of what's going on over the entire system when millions and millions of particles are colliding with each other at the same time, some of them reacting, some of them not, and the energy is very in flux in that system. So we kind of need a different model to help us see that more realistic scenario. Part 2 of this discussion involves what it looks like on a more holistic scale, with many, many, many particles in one space colliding with each other and moving around. How can we use that as a way to help us understand how a chemical reaction takes place? So we're going to be using a slightly different model for this view called a Maxwell-Boltzmann distribution. With any kind of distribution graph, it's important to remember that it's a statistical analysis of a certain proportion of molecules. It's how many molecules have a certain amount of kinetic energy out of the entire sample. So when we're looking at this particular graph here, you're looking actually at two different curves. It's the same sample of particles that could be reacting with each other, and one of them's at a higher temperature and one of them's at a lower temperature. Remember that temperature is defined as the average kinetic energy of a sample of particles. So it doesn't mean that any single molecule or that all the molecules have the same exact kinetic energy. There are some high kinetic energies and some low ones, and the temperature that we measure is the average representation of that. So there's a wide distribution of actual kinetic energies at any given temperature. And what we can see is that the higher the average temperature is, the more variation in temperatures there ends up, more variation in kinetic energy there ends up being. Because more collisions are happening, more particles have a chance to speed up and then slow down. So it flattens the curve of this barrier, this graph. And as what you can see happens is as it flattens, more and more particles have the ability to reach beyond the minimum energy barrier, which is drawn in here in a dotted line. That's the activation energy. At lower temperatures, only a small fraction of the particles can collide with enough force to react, the ones that have the very highest energy out of that sample, which is obviously not where the temperature is. The temperature is sort of a lower value, that's the average. But at a higher average, you get more particles able to overcome that barrier. So temperature is a really big factor in encouraging molecules to react with each other. So if we're looking at these graphs, what we can examine is that temperature can be a way to increase the rate of reaction. As the temperature goes up, a bigger fraction of molecules have the ability to overcome the activation energy barrier, and therefore the entire reaction rate increases. And that's really one of the more powerful things that you can do when you're examining holistic many particle models like the Maxwell-Boltzmann distribution, is you can examine a rate. For a single particle collision causing a single product to occur, it doesn't really have a real-time component to it. But with a large sample of particles, you can measure how many particles are reacting, how many are turning into products, and how many are not in a given amount of time. So it really can be a more analytical way to examine a chemical reaction as it takes place. There is some math that you can apply to these as well. The fraction of the molecules that can react under this curve here has its own logarithmic function. As you can see, it's kind of a curvy line there. Natural logarithm that is based a lot on the activation energy barrier, but also the temperature. So this would be the mathematical model that would represent the amount of particles that are needed to, or that are colliding at a certain energy to react with each other. So from here, what we're going to be doing is now starting to look a little bit more at the how of a chemical reaction. What exactly is it about the bonds that are breaking? How much energy is needed to do that? And how much energy is released when the new bonds form? And then we can compare different reactions to each other. So for this first week of chemical reactions, it's about understanding this fundamental collision factor and of different ways that we can model it and look at it statistically, but also in proportion with energy. So keep in touch for next week when we continue to examine chemical reactions at a